Have you ever thought about how much of our world depends on things sticking together? From the simplest household glue to advanced industrial bonding systems, adhesives are everywhere, quietly holding structures, products, and devices in place. Yet, despite their importance, most traditional adhesives are designed for dry, controlled environments and often rely on synthetic, petroleum-based chemicals. But what happens when bonding needs to occur in far more complex conditions, like inside the human body, on wet biological tissues, or in environmentally sensitive settings? This is where bioadhesives begin to redefine what adhesion really means. Bioadhesives are a class of materials derived from natural sources or inspired by biological systems, designed to bond surfaces together in ways that conventional adhesives cannot. Unlike standard glues, bioadhesives are often capable of functioning in wet, dynamic, and chemically complex environments. This unique capability makes them especially valuable in fields such as medicine, biotechnology, and sustainable materials engineering. At their core, bioadhesives represent a shift from purely synthetic design toward materials that are either directly sourced from nature or engineered to mimic natural adhesion mechanisms. Nature itself provides some of the most powerful examples of adhesion. Consider mussels, which can attach themselves firmly to rocks in turbulent ocean environments where waves, salt, and moisture constantly challenge their grip. Or think about geckos, which can climb vertical walls and even hang upside down thanks to microscopic structures on their feet. These natural systems have evolved over millions of years to achieve reliable adhesion under conditions that would render most synthetic adhesives useless. Scientists study these organisms not just out of curiosity, but to understand the molecular and structural principles behind their adhesive abilities. This approach, known as biomimicry, has become a driving force in the development of next-generation bioadhesives. One of the most transformative applications of bioadhesives is in the medical field, where the ability to safely and effectively bond biological tissues can significantly improve patient outcomes. Traditional wound closure methods such as sutures and staples, while effective, can cause additional tissue damage, increase the risk of infection, and require removal or follow-up procedures. In contrast, bioadhesives offer a minimally invasive alternative. They can be applied directly to tissues, conform to irregular surfaces, and form strong bonds even in the presence of blood or other bodily fluids. Some bioadhesives are also designed to be biodegradable, meaning they gradually break down as the tissue heals, eliminating the need for removal. In addition to wound closure, bioadhesives are being explored for applications such as sealing surgical incisions, attaching medical devices, and even delivering drugs in a controlled manner. The materials used to create bioadhesives are as diverse as their applications. Many are based on naturally occurring polymers, including proteins and polysaccharides. For example, gelatin, derived from collagen, offers excellent biocompatibility and flexibility, making it suitable for soft tissue applications. Chitosan, obtained from the shells of crustaceans, is valued for its antimicrobial properties and ability to promote wound healing. Alginate, extracted from seaweed, can form hydrogels that provide both adhesion and moisture retention. These natural materials provide a strong foundation, but they are often further modified through chemical or physical processes to enhance their performance. By adjusting molecular structures, researchers can control properties such as adhesion strength, elasticity, curing time, and resistance to environmental factors. Beyond healthcare, bioadhesives are gaining attention in a wide range of industries that are seeking more sustainable and environmentally friendly solutions. In packaging, for instance, there is a growing demand for adhesives that can replace conventional synthetic glues, which are often difficult to recycle and contribute to environmental pollution. Bioadhesives made from renewable resources offer a promising alternative, as they can be designed to degrade naturally without leaving harmful residues. In personal care products, bioadhesives enable the development of skin-friendly formulations for applications such as wearable patches, cosmetic products, and transdermal delivery systems. Even in electronics, where flexibility and miniaturization are becoming increasingly important, bioadhesives are being used to assemble components in ways that traditional rigid adhesives cannot support. Sustainability is one of the key factors driving innovation in this field. As global awareness of environmental issues continues to grow, industries are under increasing pressure to reduce their reliance on fossil fuels and minimize their ecological footprint. Bioadhesives align with these goals by offering materials that are not only derived from renewable sources, but also designed with end-of-life considerations in mind. This means they can break down more easily in natural environments, reducing long-term waste and pollution. However, achieving the right balance between performance and sustainability is not always straightforward. In many cases, bioadhesives must match or exceed the strength, durability, and reliability of traditional adhesives while maintaining their environmental advantages. Despite their potential, bioadhesives still face several challenges that must be addressed before they can achieve widespread adoption. One of the primary challenges is mechanical performance, particularly in applications that require high load-bearing capacity or long-term stability. While significant progress has been made, some bioadhesives still fall short of the strength provided by conventional industrial adhesives. Another challenge lies in scalability and manufacturing. Producing bioadhesives in large quantities while maintaining consistent quality and cost-effectiveness can be complex, especially when dealing with natural raw materials that may vary in composition. Additionally, ensuring long shelf life and stability under different storage conditions is an important consideration for commercial applications. Fortunately, advances in material science, nanotechnology, and bioengineering are rapidly addressing these limitations. Researchers are developing hybrid systems that combine natural and synthetic components, aiming to achieve the best of both worlds. These innovations are leading to bioadhesives with improved strength, faster curing times, and enhanced resistance to environmental stress. At the same time, new fabrication techniques are making it easier to produce these materials at scale, bringing them closer to practical real-world use. Looking ahead, the future of bioadhesives is incredibly promising. The field is moving beyond simple bonding solutions toward multifunctional materials that can respond to their environment, deliver therapeutic agents, or even actively participate in biological processes such as tissue regeneration. This evolution reflects a broader trend in science and engineering, one that emphasizes integration with natural systems rather than opposition to them. By learning from nature and applying those lessons through advanced technology, we are not only improving how materials perform, but also redefining what they are capable of achieving. In the end, bioadhesives are more than just an alternative to traditional glue. They represent a new way of thinking about materials, one that prioritizes adaptability, compatibility, and sustainability. As research continues and new breakthroughs emerge, these materials have the potential to transform industries ranging from healthcare to manufacturing, all while reducing environmental impact. So the next time you think about something as simple as sticking two surfaces together, remember that the future of adhesion may not come from a factory alone, but from the intricate and powerful designs found in nature itself.